Okay, here we go. The rest of section 14. Recording might come out a little on the long side, but well, after all, it's a recording. If it's longer than you want, you can stop it and come back later. Where I had left off is right here where it says heat engines. Okay, what I had done so far is I'd gone through the underlying physics, the first and second laws of thermodynamics, and some things related to that. So now we're going to apply some of this to devices which convert heat into mechanical work. The original example, of course, being a steam engine, where you build a fire underneath the thing and it ends up making some sort of machinery run. Today, there are a number of different types of heat engines. You've got internal combustion engines like gasoline and diesel engines. You've got the jet engines on a plane. You've got steam turbines like you have in many electric power plants. Any of these things would be examples of heat engines. Now, any of these devices that I was just naming off, or even some examples I didn't name off, have to do three basic things. They have to take in heat. So if it's a steam engine, you know, that's the fire that you build underneath the thing. And then they have to do work, because if they don't, there isn't really any point to the machine. And then not all of the heat that's taken in gets converted into mechanical work. Some of it leaves the engine again in the form of heat. And what I've done here is kind of illustrate this with a simplified example. This is, as I'm sure you will be able to tell, this is not a practical engine, the way this thing works. Rather, it's designed to have one thing happen at a time, rather than to be, you know, the most efficient or most practical in some other way. So we've got some sort of a vehicle, let's say, kind of one step up from a Fred Flintstone car. You're not pushing it along with your feet, but what you've got is you've got this cylinder mounted on it, containing some sort of a gas, air perhaps, and the piston in that cylinder is connected via some sort of connecting rods to, you can tell it's an older vehicle because it's rear wheel drive. So first thing, the state of the gas, that would be the gas inside the cylinder here. Let's say the state of the gas starts out at some original volume, and it's at atmospheric pressure, and you can read the temperature off of which isotherm the point lies on, and it starts out at room temperature. So a heat engine has to do three things. First of all, take in heat. So that's process AB, okay? We have here a heat source, which looks suspiciously like a candle. Things might go a little faster if that was a propane torch instead of a candle, but one way or another, heat is added to this system. Well, as the temperature goes up, it's going to make the pressure go up. At a higher temperature, the air molecules are shooting around in there faster, and therefore they hit things harder, and there's more pressure. So you add heat until you've driven the temperature up to the temperature I called T3. In order to do just one thing at a time, we prevent the vehicle from moving. So I've got a block under the drive wheel here, and the piston doesn't move, and therefore it's a constant volume process. Okay, this is the original volume, and at point B, it's still at the original volume. It goes right straight up on my graph. So it's taken in the heat. The next thing it has to do is, well, yeah, would have to come next, is work. So you kick the block out from under the tire, and now, because of the fact that the pressure on this side of the piston is higher than the pressure on that side of the piston, which is just atmospheric, the gas expands. The pressure difference pushes the piston outward. As it does so, that forces the wheel to turn, and your car goes a few feet down the road that way. And if we imagine absolutely ideal conditions where there's no drag between the piston and cylinder or anything else like that to hold it back, the gas would expand until the pressure in here was the same as the pressure out here. So that's process BC. The volume is increasing as it moves along there. And when it stops expanding is when the pressure returns to atmospheric pressure. Okay. And if it takes place fairly quickly, we could approximate it as an adiabatic process. An adiabat goes across the graph something like this, steeper than an isotherm. So I didn't bother to draw a third picture, but what we have to do now that the engine has completed the useful work that we can get out of this cycle, we have to get the gas back to point A so we can do it over again and make the car keep progressing down the road as this cycle repeats over and over. So the way that's usually done in any practical engine is some valve opens up and the gas that's in there is released, and that's the exhaust part of the cycle. But actually, I shouldn't say any practical engine, but that's the way it's frequently done. But actually, you don't have to get rid of the actual gas that's in there. You just have to get the heat out of it to bring it back down to room temperature. Okay. If you're not really in much of a hurry to get where you're going, you could just pack the cylinder in ice and make the gas contract again. Something a little bit like that is frequently done with electric power plants, especially nuclear power plants, because the working gas there would be steam. Okay. Well, after it's gone through the turbines, you don't want to let that steam just go up the stack because it's radioactive. What they do instead is they have a heat exchanger and they condense the steam back into water and pump it back into the boiler again. So that radioactive water just goes around and around and around without ever leaving the power plant. The reactor boils it, the steam spins the turbines. After it's done that, you condense it back into a liquid, pump it back into the boiler, and the cycle repeats. And then you've got these big cooling towers. Okay, so on the other side of the heat exchanger is some more water that's not radioactive, and that water evaporates, and that's what keeps that water cool. Okay, you have these, especially in humid weather, you'd see these big clouds of vapor coming up out of the cooling towers. And actually cooling towers like that are sometimes used for power plants that burn fossil fuels also, something that's burning coal or some other thing like that. If it's located on a stream where you don't want to be dumping large amounts of heat into the stream because you kill all the fish and the environmentalists get mad at you that way. Not to mention people who like to fish. And so they'll build these cooling towers for the same reason, is to get rid of the plant's waste heat without having to dump it into the environment in a harmful way. So what you really have to do to get from point C back to point A is remove some heat to bring it from T2 back down to room temperature. Once you're back to point A, you get out your propane torch again, or maybe your candle, and it goes around this cycle on the PV graph over and over and over again. So it's heat, not gas, that you actually have to get rid of during the, what you might think of as the exhaust part of the cycle. Now earlier, that was probably back in section 13, I had said that the area under the curve on a PV graph, the area underneath it is the amount of work done. Well, if you've got a cycle like this, the total work done for the entire cycle is the area enclosed within it. Okay, let's go through this cycle again a step at a time. AB, the graph is a vertical line, and there isn't any area underneath a vertical line, so no work is done, which kind of makes sense because the piston doesn't move, and therefore the car doesn't move down the road any. No work is done. For parts BC, well, work is the area under the curve, or the way we defined it. See, the textbook makes kind of an awkward transition at this point. In the previous chapter, they're talking about the work done on the gas. And then when you get into this discussion of engines, it's more convenient to talk about the work done by the gas rather than the work done on the gas. So if you're going to make that switch, the work becomes P times dV instead of negative P times dV. So that, you know, the work done by the gas would be the same thing as the energy output of the engine. And people talk about it that way so that you don't have some annoying minus sign on your numbers all the time. So anyhow, if you're going to look at it that way, the work done by this gas, meaning the energy it delivers to that wheel, then when delta V is positive, P time, well, all the little dV's under that curve, maybe I should say. The change in volume is positive, so the work is positive. And so the work done in that part of the cycle is this shaded area here. But then as you go from C back to A, now the volume is decreasing. So P times delta V is negative. And when you add up all the work for the entire cycle, well, this minus that would be the area inside of the cycle, like I shaded here. So net work is the enclosed area for any kind of an engine. And I think at the top of the next page, I've got an example. Yes, a not at all realistic example, obviously rigged up so that somebody can do that with some fairly elementary mathematics. Any kind of realistic cycle, you'd have curved sides on the diagram and you'd have to integrate. But just to keep it short and sweet, we'll do one where it's just a rectangular cycle on the picture, and that goes like this. So it's a rectangular area, and the area inside of a rectangle is its length times its width, or I guess I called it length times height. Well, length times width, length times height, whatever you want to call it. That's the formula for the area in a rectangle. So the length, get this back where you can see it. If by length I mean the change in volume, well, if one end is at 3 and the other end is at 8, that means 8 minus 3, the length of this thing is 5 cubic meters. And for the height of it, If the bottom is at 2.0 times 10 to the fifth pascals, and the top of it is at 2.5, 2.5 minus 2, the height of it is 0.5 times 10 to the fifth pascals. A pascal is the same thing as a Newton per square meter. So half of 5 is 2.5. Hopefully you didn't need a calculator for that one. Cubic meters, square meters cancels down to just newtons times meters, better known as a joule. So that's the work done by the engine as it goes around one complete cycle. The energy flow through any kind of an engine, whether it's the engine on your lawnmower or whether it's the jet engine on an airplane or anything else, it's probably clearest if you think of this in terms of a steam engine, though. As I said earlier, obsolete technology is kind of nice because it's simpler. But any kind of an engine has to get its heat from somewhere. In a steam engine, this would be the boiler. Okay, you've got this big container full of steam at some elevated temperature. In the case of an internal combustion engine, the hot reservoir is not quite so neatly defined, but it would be the burning fuel inside the cylinders. That's the heat source there. For any practical engine that I've ever heard of, the cold reservoir is the surrounding environment. And heat flows naturally from a hot place to a cold place. And you can, what a heat engine does is it taps into that natural flow and diverts some of the energy as useful work. There's an analogy I kind of like. Just as heat has a tendency to flow from high to low temperature, water has a tendency to flow from high to low elevation. So what they used to do many, many years ago is they'd find a nice place where there's a stream, and the stream kind of runs downhill like that. And they'd build, I think they called it a sluiceway, it was like this chute that the water would run into the one end up here on the stream, and over here on the other end, you'd have the water spilling out. And you see you'd have a big wheel on the side of your mill here, pivoted right. There'd be lots of little bucket-like things to catch the water. And so the falling water would, I should have made my sluiceway a little longer. I think it would probably work better if the water came out over here. But the point is, as the water flows from high to low elevation, this device taps into that natural flow to create useful work, okay? This shaft here might be connected to some big grinding wheel that would grind up some grain and make it into flour, or do some other useful task like that. Well, like I said a minute ago, heat naturally flows from high to low temperature in a very comparable way to how water flows from high to low elevation. And just as this device taps into that natural flow of water to produce useful work, an engine taps into the natural flow of heat to create useful work. Okay, so a bunch of energy is taken in from the hot reservoir. Some of it, well, its natural tendency is to flow into this cold reservoir, but you can divert some of it into useful work. Now, a quantity that anybody who has to pay to run one of these things is going to be very interested in is its efficiency. Efficiency is defined like this. Um, E for efficiency. Why not? We've only used E for 7,000 other things in this course. As far as the subscripts go, the I stands for in, and I'm going to write another thing in a minute, have some O subscripts in it, O for out. So the efficiency, not only of an engine, but really any kind of a device, the efficiency is the ratio of, well, I like to call it the ratio of what you got to what you paid for. Okay. What fraction of the energy taken in by the device actually goes to the purpose you intended? In the case of an engine, the intake of energy would be in the form of heat. What fraction of that goes to useful work? We don't do it in this class, but there's a little exercise I have some of my other classes do as a lab for this part of the course. And I just thought it might be kind of interesting to, for once, do something real instead of play around with the little toys I keep in the cabinet in my laboratory. So I have students, at least the ones who have cars available to them, I have them determine the thermal efficiency of their own vehicle. And actually, if anybody feels like doing it just for the heck of it, let me know. I mean, I can send you the directions, but basically you need three pieces of information. You need to know what the car weighs. You can either look that up on the internet or it's written on your registration stub. You need to know your gas mileage. Well, actually, I guess there's one other thing you have to determine, which is the heat of combustion of gasoline. But that's in the directions for the lab. And then I have them do a little road test to find out how much time it takes to coast from 50 to 40 miles an hour in neutral. From that you can calculate the amount of work needed to keep the car moving. And I've seen this over many years done for what is now a total of many cars, and I haven't actually kept records and done an average. But the impression is that it usually, if I had kept an average, it would probably come out around 13 or 14%. Now, and it hasn't changed that much over the years either. New cars are a little more efficient than ones from, say, 50 years ago, but it's only really changed by 1 or 2%. Nothing that really stands out, I don't think. I don't know, maybe 3%, and I just wasn't keeping that close track. But so if your car is 15% efficient, what that means is that for every dollar's worth of gasoline you put in the tank, 15 cents worth goes into pushing the car down the road. The other 85%, or the other 85 cents, just goes into heating up the outdoors, the same as if you took the gas out behind the barn and burned it, which would be something you'd want to do very carefully if you ever actually tried it. But that's what efficiency means. What fraction of the energy actually got turned into useful work? Something that's kind of goes along with that would be just a form of conservation of energy. Or another way of phrasing it would be to say it follows from the first law of thermodynamics, which is basically conservation of energy. Oh, I put the, don't write that down yet. Put the equal sign in the wrong place. better when you actually pay attention to what you're doing. I should probably try that. Okay. Input heat equals the work done plus the output heat. Okay. If you, well, energy only comes into the engine in one form. That's this input here. So that's on the one side of the equals. Energy leaves the engine in two different forms. Some of it leaves as wasted heat. Some of it leaves as useful work. So what goes in must equal what comes out. And so work plus heat out, that's over here, is equal to the heat that it takes in, conservation of energy. Here I made it 30%, a little example I wrote in the note packet. Here I made it 30% efficient instead of 15%. That would be more what you'd get like from an electric generating plant. They tend to be, well, a little better than this, 33, 35% efficient, something like that. The ones that are steam turbines. The ones that are natural gas turbines, they run a little hotter and they can get up around 40%, as I understand it. But even 40% is probably kind of disappointing. One would like one's devices to be better than 40% efficient. So what this next part of it gets into is limits on efficiency. In other words, why so terrible? Well, first of all, a limit on the efficiency of any device, whether it's a heat engine or a lever. You know, if you're a carpenter pulling a nail out of a board with a claw hammer, that hammer is basically a lever, okay? And conservation of energy says that you can't get any more work out than what you put in, okay? As you go pulling on the handle of that hammer, you're doing work on the hammer. And then the claws are pulling on the nail, and they're doing work on the nail. And conservation of energy says that the energy output in pulling the nail can't be any more than the energy that's input by you pulling on the handle. Now, many devices are, in fact, fairly close to this theoretical limit of 100%. Pulling a nail with a hammer. The main source of inefficiency there is as you pull on the hammer, where the hammer bears against the board, it has a tendency to crush the wood. So you're doing some work doing that instead of pulling out the nail. So less than 100% of your effort goes into pulling the nail. But if you did something like stick a piece of metal, you know, maybe you've got a chisel laying there and you stick it underneath the hammerhead to give it something really hard to bear against, you can get pretty close to 100% efficient. And so it is with other types of devices. Electric motors, if they're well built, can be, you know, can have an efficiency that's into the 90s of percents. Of course, you know, you can talk about efficiency of things that don't produce mechanical work either, like a transformer. Compare the amount of power going out of the secondary circuit to the amount of power coming into the primary circuit, and they can be close to 100% efficient, you know, at least into the 90s. So if all these other types of devices can have something fairly close to what's allowed by conservation of energy, why are you driving around in a car that's 15% efficient? Because when it's a heat engine, you see, I'll get back to this in a little while, but out of all the different types of energy, heat is kind of unique. When heat is involved, there is a second lower limit placed on efficiency by the second law. Conservation of energy is basically the first law, and that limits hammers and electric motors and transformers and a lot of other things. Heat engines in particular are limited by the second law. The maximum allowable efficiency is called the Carnot efficiency after Sadi Carnot, who figured all of this out about 200 years ago. And it, well, it basically goes like this. And maybe I'll get a clean sheet of paper. I'm not sure it's all going to fit. Maybe it will, but this is just a bunch of old clean sides anyhow. So the Carnot efficiency. Let's assume that these reservoirs are large enough to maintain a constant temperature, okay? You draw a little heat out of the hot reservoir, well, you know, maybe you pull 1,000 joules out of there, but the internal energy of that thing is 100 million joules, and you're not going to miss 1,000 joules. And you know, it's a really big reservoir. This will simplify the math. So let's assume that both the hot and cold reservoir maintain a constant temperature. A fairly accurate assumption for something like a steam engine. The boiler maintains a fairly constant temperature because as you use the steam, the fire in the firebox makes more. And anyhow, what I want to do is I'm going to calculate the change in entropy of the hot reservoir, and I'm going to calculate the change in entropy of the cold reservoir. And when you add them together, that would be the change in entropy of the entire world due to running this machine. So first of all, good a place to start as any, the hot reservoir. Well, here's where the assumption of a constant temperature comes in. If T is a constant, then I can take it out in front of my integral. Of course, there's a somewhat more elaborate version of the same argument that you can go through where you don't assume a constant temperature, but well, let's keep it short and sweet. So I already did an example where it went kind of like this before. The integral of dq just gives you q, and in this case, it'll come out negative. As we've seen going back into physics 131, when I talked about heat a little bit back then, heat is positive when the system is gaining heat. Heat is negative when the system is losing heat. So the hot reservoir is losing heat, and therefore its entropy decreases, and it would be decreases by this much. For the cold reservoir, it's the same thing all over again, except with a plus sign because it's gaining heat. So heat goes in, positive. Heat goes out, negative. The subscripts, O for output, I for input, like I wrote down somewhere on the previous page. So the total change in entropy that occurs from running this engine minus the 1 plus the other and the second law says that entropy cannot spontaneously decrease. Delta S must be greater than or equal to 0. So let's work with that equation for a little while. I'm going to take the output term over to the other side. And then I'm going to kind of reshuffle things. I'm going to divide both sides by QI, and I'm going to multiply both sides by TO, so then it'll look like this. And then, for no apparent reason, I'm going to add 1 to both sides. Oh, lost a minus sign. I've been telling you all along, minus signs are evil. That minus sign there belongs here, and so there. Little mini minus sign. Okay. So let's go over here on the side for a moment and figure out what this thing with the Q's in it is equal to. I had said a few minutes ago, and maybe I should have used EFF for efficiency instead of just plain E. It looks less like the charge on an electron that way. Here, you know what? Let me just, there's lots of room on this previous page. I'm going to take that one and rearrange it so it says QI minus QO is equal to the work. Okay, and I'm going to put that in there for W. So heat in minus heat out, the difference between the two is the work that the thing did. Well, QI divided by QI is 1. And that, somewhat more neatly written, is the thing I had there. So the moral of the story is, if this was one of Aesop's fables, the moral of the story is that efficiency can be at most 1 minus the ratio of the temperatures, okay? Input temperature, that's another way of saying the temperature of the hot reservoir. And TO, output temperature, that's another way of saying the temperature of the cold reservoir. The efficiency has to be less than or at best equal to this expression here. So maximum efficiency of a heat engine, 1 minus the ratio of the temperatures. Okay, so the second law has nothing to say about these other devices. There's no heat flow through a hammer, but imposes this lower theoretical limit on the efficiency of a heat engine. And somewhere, well, that's on the next page. Okay, we'll get to that then. But first, an example. So I think we had another example, maybe in section 13, with the same steam locomotive here. You've got the superheated steam coming into the cylinder at this temperature, and then it leaves the cylinder and goes up the stack at that temperature. And so what is the maximum possible efficiency of this engine? So that is just a matter of sticking numbers into this. There is, of course, as there often is, there is one little booby trap waiting to catch you, which is that just like all the other expressions in this part of the course, this is the absolute temperature. You have to convert to Kelvin, just like in PV equals nRT and all of this other stuff I've been flinging around for the last week and a half or whatever it's been. So for number 4, I'll just drop the numbers into that. The output temperature, the steam leaves the cylinder at 105 degrees Celsius. You have to add 273 to get Kelvin. And it entered at 250 degrees, and you have to add 273 to make that into Kelvin. So 1 minus, this is 378 Kelvin over 523 Kelvin. You divide the answer is 0.277. Or a lot of people prefer to express such things in percents rather than as decimals. If you like percents, you would call it 27.7%. Now, one thing I don't want anybody confused about, this is not the actual efficiency of this steam engine. This is the theoretical ceiling, the theoretical upper limit for an engine operating between these temperatures. Now, first of all, as it says on the next page in the note packet, this is the efficiency of the Carnot cycle. I might as well flip it over now. It's possible to show, it's not a terribly lengthy derivation, but I've done enough of that lately, so I'll just state it. But it's possible to show that an engine operating around this cycle has this maximum possible efficiency given by this formula. You've got, if you start at point A, it goes along an isotherm and then an adiabat, and then back along an isotherm and back up an adiabat. In other words, isothermal and adiabatic processes. And from there, the cycle can repeat. And that will be this efficient. Now, a steam engine does not go around the Carnot cycle. A steam engine follows what's called the Rankine cycle, which is a different shape that doesn't have as much area inside of it. That's going to bring the efficiency down some from this. And then after that, you can start talking about friction in the bearings and practical considerations like that. So even though theoretically it could be as much as 27.7% efficient, the actual efficiency of a steam locomotive is, I believe, somewhere in the same general neighborhood as I was talking about for your car, somewhere in the low teens. So friction, shortcomings of the design, etc., cause further reductions in efficiency below this theoretical maximum. A less mathematical way of looking at it. Okay, here we got all kinds of nice formulas that prove that you're limited to something less than 100% efficient, but a conceptual argument rather than an analytical type one. Let's say you build an air conditioner and sat it in the window of your living room. Now, an air conditioner is a heat pump. I was talking the other day about how heat pumps work, but it basically turns your house into a refrigerator. It's the same basic principles as the refrigerator in the kitchen. So it pumps heat from the inside of the house to the outside of the house. Heat, like water, will only spontaneously flow toward a lower height. Heat will only spontaneously flow toward a lower temperature, but you can pump them the other way. If you've got a pump, you can, like if you've got a well at your house, the water level in the well is lower than the level of your bathtub, but you can pump the water up to the bathtub. And in a similar sort of way, you can pump heat in the opposite direction from where it wants to go. So you've got 70 degrees Fahrenheit in your living room, and you've got 90 degrees Fahrenheit outside, and you can pump heat from your living room to the outside. Now, in any actual air conditioner I've ever seen, what operates the heat pump is an electric motor. You have to plug the thing in. But let's say you got the idea for a heat pump at the other end of the box here. You got this metal box that's the air conditioner you're setting in your window. And instead of having to plug it in, the heat pump is driven by a heat engine. And let's say that the heat engine uses the hot air outside your house for its hot reservoir, and it uses the cold air inside your house for its cold reservoir. Now, let's think about what would happen if this engine could be 100% efficient. Back to the diagram with the big arrows on it. If an engine is 100% efficient, that means 100% of this heat that it takes in goes over here as useful work. 100% here, none of the energy goes there. So that means that this heat engine takes in a bunch of energy from the outside, the hot air outside, and uses all of it to run this heat pump. None of it gets dumped into your living room. Meanwhile, the heat pump is pumping heat out of your living room. And the problem here is that you have just figured out a way to make heat flow spontaneously, because you see, you don't have to plug this in, or you don't have to put gasoline in it or anything. It's just a box that you set in your window and makes heat go from someplace cold to someplace hot without any kind of outside assistance. You have just invented a pot of water that freezes when you sit it on a stove. So it won't work. You just think you've invented a pot of water that freezes when you put it on a stove. So clearly the efficiency of an engine has to be less than 100% to avoid violating the second law of thermodynamics. And even if the engine is somewhat less efficient, I mean, what if it's 90% efficient or 80% efficient? There's still a problem as long as the heat that this dumps into your living room is less than the amount of heat that this thing pumps out of it. You still have a net flow of heat in the wrong direction. So when you get into the details, it turns out that the engine can't be any more efficient than this. Otherwise, it could be used to violate the second law. You could make heat flow spontaneously in the wrong direction. And actually, the same theoretical limit applies to heat pumps also. In fact, unlike something that goes around the Rankine cycle, a steam engine, or unlike the gasoline engine in your car, which uses the Otto cycle, the Carnot cycle is reversible. All you have to do is turn these arrows around, and now you've got a heat pump instead of a heat engine. And so anyhow, engines or heat pumps, any device that has heat flowing through it is limited by the second law and can't be any more efficient than that. 27% indicate. What this means is the hotter an engine is, the more efficient it can be. Okay, that's the takeaway concept. Is the hotter you can run an engine, the better, because you see, if you make the hot reservoir a really big number, then this fraction becomes, there isn't too much you can do about the numerator here, because, well, you could get it a little colder than this. That's what's done, for example, when you've got turbochargers on the exhaust stream of a gasoline engine. You're extracting some more heat from the exhaust. But you get this too much lower and you come up against room temperature, and that's kind of your limit there. So the possibility for improved efficiency primarily comes from making the input temperature higher. If this denominator is a really big number, then this fraction becomes a small number, and you're not subtracting as much off the one, and you get a bigger efficiency that way. So, for example, I had mentioned earlier that natural gas turbines are a little more efficient than steam turbines because they run hotter. This number's bigger. The most efficient engines I've ever heard of are rocket engines. They're really hot. They don't quote me on the numbers, but I want to say they can be something like 60 or 70% efficient. Again, because of the implications of this formula right here. Well, let's see, what's left to talk about? We're getting down there. There's the Carnot cycle. So, number 5, last example in the whole course. So, like I said, this is just the theoretical limit. This steam engine's true efficiency, when you take all that other stuff into account, is only 14%. So if 100,000 watts, 740, here, wait a second, 100,000 divided by 746, it's 134 horsepower engine, if you prefer to think of it that way. If that's the amount of horsepower you want to be getting out, then how much, find the energy taken in. How much energy is it going to have to take in each second to produce that desired output? So that's it just uses these. I'm going to back up and use this other sheet of paper here because it just uses these formulas that are conveniently right there. So if the efficiency is the work done divided by the heat taken in, well, one of the things the question asks for is the heat taken in. And we know both of the other things, so we can just kind of rearrange it like this. Heat in equals the work divided by the efficiency. Now, when you do this kind of thing, the efficiency has to be a decimal, okay? I had my 27% here, and you don't want to be doing that. You want to be doing 0.277. And, well, the figure here is 14%. That's got to be 0.14. If you stick 14, your answer will be off by a factor of 100. So the work we want to get out in 1 second, okay, in 1 second, 100,000 joules over the efficiency 0.14. Now the question said 100,000 watts. Remember what a watt is. By definition, a watt is a joule per second. So 100,000 joules per second, better known as 100,000 watts. And the question says each second, so the time interval we're talking about is 1 second. Seconds over seconds cancels, and the work is 100,000 joules. So you divide that, and the energy that it needs to take in from its fuel each second is 714,000 joules to get the 100,000 joule output. As for how much is given off as wasted heat, well, that would be the conservation of energy thing that I was talking about here. If a total of 714,000 joules goes in, a total of 714,000 joules has to go out. 100,000 goes out as work. That leaves 614,000 that must have gone out as wasted heat. That's the basic idea behind it, to write out the details. If heat in equals the work plus, I just can't seem to do the plus sign in that equation for some reason. Rearranging that gives that the output heat, the exhaust heat in other words, you just subtract the W from both sides. So some final comments. So I said something earlier about how heat is kind of unique compared to other types of energy. What's so special about heat? Because after all, other kinds of energy can be converted to each other, in principle at least, with an efficiency of 100%. If you've got a ball and you drop it, it starts out with 100, with some potential energy, MGH. As it falls, that potential energy gets changed into kinetic energy. And if you create optimized conditions by having it fall through a vacuum, 100% of the potential energy you started out with will be converted into kinetic energy by the time it reaches the floor, 100%. And this is typical of almost all kinds of energy. Electrical energy can be converted into kinetic energy and so on and so on. But not heat. So, in fact, get the formula back. People who like to think long term and wonder about what's going to happen to the universe in the distant future, well, every day more heat flows from hot places to cold places, like heat leaves stars and goes to the surrounding cold space. So if you wait quite a long time, I mean, maybe 1 trillion years or something like that, uh, it's possible that the universe could reach thermal equilibrium after all the last of the stars run out of fuel. And I'm leaving out a number of other cosmological things that are going on here, but um, if that were to happen 1 trillion years from now, if everything in the universe was at a perfectly uniform temperature, then for anything that qualifies as a heat engine, including your own body, by the way, if the output temperature is equal to the input temperature, the maximum possible efficiency would have become 0, which means that at that point, life itself would become impossible, as well as any other kind of mechanical activity and mechanical work. And they refer to that as a heat death if that was to happen. Um, well, that may or may not actually happen. What the end of time looks like is still unresolved at this point. But anyhow, at that point, 1 trillion years from now, if that was to happen, the universe would contain all the energy it contains today. Conservation of energy says you can't get rid of it. If you add up all the different kinds of energy, you still have to get the same total that you had today or 1 billion years ago, for that matter. But all of that energy would have been rendered unusable because entropy would have reached a maximum. So if converting energy into heat degrades it like that, what's so special about heat? Well, it's because thermal energy is associated with disorganized motion. Consider, for example, a bullet flying along through the air. That's rather organized. All of those lead atoms are moving along perfectly parallel lines, and they're all moving at exactly the same speed, okay? So the kinetic energy of all those individual atoms has been very highly organized. Well, now, let's say the bullet runs into a big fat tree that's been standing there for 200 years, and it burrows into the wood and stops. Where did all the kinetic energy go? It was converted into heat by friction. The bullet and the surrounding wood have been raised to a higher temperature. What all the atoms and molecules are doing now is, first of all, they no longer have exactly the same speed. If you draw a graph, it's a topic I skipped over called the Maxwell speed distribution, but the N for the number of molecules, V for their velocity, it's one of these lump-shaped curves, kind of like that, okay? So the temperature corresponds to the root mean squared speed, which should be right about there someplace. But you've got a whole distribution of speeds. Instead of having all those atoms moving at exactly the same speed like they did when the bullet was flying along through the air. And furthermore, the directions have also been randomized. One molecule is vibrating in this direction and another molecule is vibrating in that direction, and they're all kind of mixed up and randomized. And randomized things do not spontaneously change back into organized things. That's one of the implications of the second law. You don't shake up a shoebox full of pennies and find that they're all heads and no tails when you're done. And this is the reason why, as you're walking along through the woods a few months later, you don't have to worry about that bullet popping back out of the tree by getting colder. This disorganized thermal energy can never be converted, at least it can't be entirely converted, back into more organized kinetic energy, because that would represent a spontaneous decrease in entropy. And maybe one final thought that I'll share with you. Uh, Thermodynamics I think it's economics they call the dismal science, isn't it? But thermodynamics deserves the title too. You've got some clever person once, here, I'll give you one more look at me because I'm done writing stuff down. And like I said before, looking at my hands must get kind of dull. So some clever person once compared, they phrased the laws of thermodynamics, comparing them to games of chance, because after all, especially the second law is all about the statistics of the situation. So first law says you can't win, okay? It's like if you go to Las Vegas, you're not going to leave the table with more money than you walked up with, okay? The first law says you can't leave the table with more energy than you came with. Conservation of energy. So you can't win. The second law says you can't even break even. The second law says some of the energy has to be converted into heat, which is a form where you can't use it anymore. And the third law, which I haven't really mentioned before, but the main implication of the third law is that you can't actually achieve a temperature of absolute zero. You can get really close. There's laboratories today where they've gotten down into, I think it's the nanokelvins, but the closer you get to absolute zero, the harder it becomes to remove the tiny amount of thermal energy that's left. So you can only approach absolute zero asymptotically. You can't actually get there. So third law of thermodynamics, you can't quit, as in thermal motion never completely stops. So you can't win, you can't even break even, and you can't quit. That's the first, second, and third law of thermodynamics. So now that I've left everybody really depressed, I'm going to wish you the best possible summer anyhow. As I'm recording this right now, actually, what is today's date? It's actually only April 8th. I thought I'd get all these recordings taken care of as quickly as I could. And at this point, it's kind of unclear what the summer is going to look like. I don't know if we'll be able to do anything fun or if that's all still going to be closed. So maybe we'll all just be stuck inside our houses looking out at the good weather and wishing we could like go to, well, anywhere. So hopefully they'll have figured out some way that won't, I don't think we'll be completely off the hook by the end of summer, but hopefully they can open things up a little bit at least, because otherwise we're all in for a summer that's about as depressing as the laws of thermodynamics. Good luck on the final.